Hello everyone, I'm going to discuss file system internals, and this is the chapter 15 of operating system concepts. The following topics will be covered from the file systems, and then we'll talk about file system mounting, partitions and mounting, file sharing, virtual file systems, remote file systems, consistency semantics, and finally NFS. At the end of this chapter, you're going to delve into the details of file systems and their implementation. You will be able to explore booting and file sharing, and finally you'll be able to describe remote file systems using the NFS as an example. So in this chapter, we explore in detail ways to structure the file use and to allocate storage space to recover freed space, and then we will track the locations of the data and to interface other parts of the operating system to secondary storage. So as we have seen in the preceding chapters, general purpose computers system can have multiple storage devices, and those devices can be sliced into partitions, okay, and these partitions can hold file systems. So depending on the volume manager, a volume may span multiple partitions as well. Okay, so as shown in this typical storage device organization, a typical computer system can have varying number of file systems, and as you can see from here, there are 3 storage devices. And these storage devices can be partitioned in a number of volumes, such as partition A, partition B, partition C, and partition D. Alright? In the next slide, you will see example mount points and file system for Solaris. Okay? So this is a typical mount points. So you can see some examples of the Solaris different file systems such as UFS, DevFS, MNTFS, TMPFS, OBJFS, and then we have the UFS, CFS. So lots of file systems. The TMFS that you see here is a temporary file system which is created in a volatile main memory. So that is why it's called temporary file system. And its contents are erased if the system reboots or crashes. The OBJFS, or a virtual file system, essentially it's an interface to the kernel that looks like a file system, and it gives debuggers access to kernel symbols. The CTFS here that you see is a virtual file system that maintains contract information to manage which processes start when the system boots and must continue to run during the operation. Another example of the file system is the LOFS, or the LOFS. It's a loopback file system that allows one file system to be accessed in place of another one. The proc file system, okay, it's a virtual file system that presents information on all processes as a file system. And the UFS and the CFS that you see here are general purpose file systems. So the file systems of computers can be extensive, and even within a file system, it's useful to segregate files into groups and manage and act on those groups. And the organization involves the use of directories. So you see here the directory structure and the appropriate file systems. Now, just as a file must be opened before it can be used, a file system must be mounted before it can be available to process or to processes on the system. And more specifically, the directory structure may be built out of multiple file system containing volumes, which must be mounted to make them available within the file system namespace. The amount or the mount procedure is straightforward. The operating system is given the name of the device and the mount points. Okay, so the mount point is the location at which they can be accessed, no? It's the location within the file structure where the file system is to be attached. And some operating systems require that a file system type to be provided, while others inspect the structures of the device and determine the type of the file system. And typically, a mount point is an empty directory. For example, in Unix system, a file system containing a user's home directories might be mounted as /home. Okay? Then to access the directory structure within that file system, we could precede the directory names with /home as, for example, /home/ the name of the user. So mounting that file system under /users would result in the path name /users and then the name of the user, which we could use to reach the same directory. So basically, a partition can be a volume containing a file system, or we call it the cook file system, or the raw system file, or we call it just a sequence of blocks with no file system. The boot block can point to a boot volume or bootloader set of blocks that can contain enough code to know how to load the kernel from the file system. Or it can be a boot management program for multi-OS booting. The root partition that we see here contains the operating system and other partitions that can hold other operating systems. Or it can be other file systems, or it can be a raw file system as well. So this root partition is mounted at boot time. Okay, and then other partition can mount automatically or manually on mount points. So we discuss about mount points. So the mount point is the location within the file structure where the file system is to be attached, or the location at which the partition can be accessed. At mount time, file system consistency is checked, and the following are the parameters. For example, is all metadata correct? If not, the operating system will fix it and try again. And if yes, the metadata will be added to the mount table and to be able to allow the access of the partition. Now, to illustrate file mounting, consider the file system depicted in these illustrations, where the triangles that you see here are the subtrees of directories that are given here. No? Figure A shows an existing file system, while figure B shows an unmounted volume residing on this particular device or disk. Okay, and this is an example of the Unix file system directory tree, while B is the unmounted file system and C is the illustration after mounting, which we can see here the existing directory tree. Alright, now the ability to share files is very desirable for users who want to collaborate and to reduce the effort required to achieve a computing goal. Therefore, user-oriented operating systems must accommodate the need to share the files in spite of the inherent difficulties. And in this section, we examine more aspects of file sharing, and we begin by discussing general issues that arise when multiple users share files. Okay, and then once multiple users are allowed to share files, the challenge is to extend sharing to multiple file system, including remote files, and then we discuss the challenge as well. Okay, so finally we can consider what to do about conflicting actions occurring on shared files. Now, for instance, if multiple users are writing to a file, should all the writes be allowed to occur? Okay, and or should the operating system protect the user's actions from one another? So basically, we're talking about permissions, protections that must be implemented and must be accurate, because most systems provide concepts of the owner and group member mechanism. Okay? Now, to implement sharing and protection, the system must maintain more file and directory attributes than are needed on a single user system. And although many approaches have been taken to meet this requirement, most systems have evolved to use the concepts of file or directory owner or user group. And the owner is the user who can change the attributes and grant access, and who has the most control over the file. Now, the group attribute, okay, defines a subset of users who can share access to the file. Okay, for example, the owner of a file on a Unix system can issue all operations on a file, while members of the files group can execute one subset of those operations, and all other users can execute another subset of operations. The owner and group member, they have what we call identifications for a given file or directory, and they are stored with the other file attributes. So when a user requests an operation on a file, the user ID can be compared with the owner attribute to determine if the requesting user is the owner of the file. Likewise, the group IDs can be compared, and the result indicates which permissions are applicable. And the system applies those permissions to the requested operation and allows or denies it. Many systems have multiple local file systems, including volumes of a single disk or multiple volumes or multiple attached systems. And in these cases, the ID checking and permission matching are straightforward once the file systems are mounted. But consider an external disk, for example, that can be removed between systems. So we have to take care of the IDs that should match between the systems when devices move between them, or that file ownership is reset when such a move occur. Okay, next is the virtual file systems. So as we have seen, in modern operating systems, support for multiple types of file systems are a thing. Okay, but how does an operating system allow multiple types of file systems to be integrated into a directory structure? And how can users move between file types or file system types as they navigate the file system space? Okay, an obvious but suboptimal method of implementing multiple types of file systems is to write directory and file routines for each type. Instead, most operating systems, including Unix, use object-oriented techniques to simplify, organize, and modularize the implementations. And the use of these methods allows very dissimilar file system types to be implemented within the same structure, including network file systems such as NFS. So users can access files contained within multiple file systems on the local drive or even on file systems available across the network. So the VFS, or the virtual file system on Unix, provide an object-oriented way of implementing the file system. So VFS allows the same call interface, or the API, to be used for different types of system. So what it does are the following functions. So it separates the file system generic operations from their implementation by defining a clean virtual file system interface. And several implementation for the VFS interface may coexist on the same machine, allowing transparent access to different types of file systems mounted locally. The second function is that it provides a mechanism. Okay, it provides a mechanism for uniquely representing a file throughout a network. And the VFS is based on a file representation structure called vnode. So the vnode is a node which hold the inodes, or network file details. So this network-wide uniqueness is required for support of network file systems, wherein the kernel maintains one vnode structure for each active node. So basically, the VFS distinguishes local files from remote ones, and the local files are further distinguished according to their file system types. Alright? Illustrated here is the virtual file system's schematic diagram, wherein we can see here that the first layer is the file system interface, and it's based on the open, read, write, and close calls, or system calls, and on file descriptors. So the second layer here that you see is the virtual file systems. As I mentioned, the VFS serves two important functions. Number one is to separate the file systems, and number two is to provide a mechanism for representing a file throughout a network. Okay, so finally we have the other layers, where we see the local file system of type 1, type 2, and the remote file system for network file systems. Now there are four main object types defined by the Linux virtual file systems. So they are the inode object, which represents an individual file, the file object, which represents an open file, the superblock object, which represents an entire file system, and the den3 object, which represents an individual directory entry. And for each of these four object types, the virtual file system defines a set of operations that may be implemented. Okay? And every object of one of these types contains a pointer to a function table. And the function table lists the addresses of the actual functions that implement the defined operations for that particular object. So for example, an abbreviated API for some of the operations for the file object includes the following examples. So int open, so this is used to open a file. The int close, then we have the parameters, which is used to close an already open file. The size tread, which is used to read a file. size twrite is used to write a file, and mmap is used to memory map a file. Okay? Now with the advent of the networks, communication among remote computers became possible, and networking allows the sharing of resources, spread across a campus or even around the world. And one obvious resource to share is data in the form of files. And through the evolutions of network and file technology, remote file sharing methods have changed. The first implemented method involves manually transferring files between machines via programs like FTP or File Transfer Protocol. The second method uses a distributed file system, or the DFS, in which remote directories are visible from a local machine. In some ways, the third method, which is the World Wide Web, is a reversion to the first. A browser is needed to gain access to the remote files, and separate operations, essentially a wrapper for FTP, are used to transfer the files. Okay? And increasingly, we also have the cloud computing, which is being used now for file sharing as well. Now, for the client-server model, remote file systems allow a computer to mount or more file system from one or more remote machines. And in this case, the machine containing the files is the server. And the machine seeking access to the file is called the client. Now, the client-server relationship is common with network machines. And generally, the server declares that a resource is available to clients and specifies exactly which resource, in this case, which files, and exactly which clients. So a server can serve multiple clients, and a client can use multiple servers depending on the implementation details of a given client-server facility. So an example of this is NFS, or the network file system. Now, in the case of Unix and its network file system, authentication takes place via the client networking information by default. And in this scheme, the user's ID on the client and server must match. If they do not, the server will be unable to determine access to the files. So consider the example of a user who has an ID of 1000 on the client and 2000 on the server. So a request from the client to the server for a specific file will not be handled properly, as the server will determine if user 1000 has access to the file rather than basing the determination on the real user ID of 2000. Now the access is granted or denied based on incorrect authentication information, and the server must trust the client to present the correct user ID. And note that the NFS protocols allow many-to-many relationships. And that is, many servers can provide files to many clients. In fact, a given machine can be both a server to some NFS clients and a client of other NFS servers. Now, to make client-server systems easier to manage, distributed information systems, also known as distributed naming services, provide unified access to the information needed for remote computing. So the domain name systems, or the DNS, provides host name to network address translations for the entire internet. And before DNS became widespread, files containing the same information were sent via email or FTP between all network hosts. So basically, that's not scalable. Other distributed information systems provide username, password, and user ID or group ID or group information methods. Okay. Then we have some examples of that. We call it the Network Information Service, which is typically used by the Oracle Corporation, which is the Sun Microsystem. Okay. And then we have the Microsoft's Common Internet File System, or the CIFS, wherein the network information is used in conjunction with user authentication, okay, and password. And this is used to create a network login that the server uses to decide whether to allow or deny access to a requested file system. And for this authentication to be valid, the usernames must match from machine to machine, as with the network file system. Microsoft also uses the Active Directory as a distributed naming structure to provide a single namespace for the users. And once established, the distributed naming facility is used by all clients and servers to authenticate users via Microsoft version of the Kerberos network authentication protocol. Okay? The industry is moving toward use of the lightweight directory access protocol, or the LDAP, and it is used as a secure distributed naming mechanism. In fact, Active Directory is based on LDAP, and Oracle Solaris and most other major operating systems include LDAP and allow it to be employed for user authentications as well as system-wide retrieval of operations or information such as availability of printers. Consistency semantics represent an important criterion for evaluating any file system that supports file sharing. And these semantics specify how multiple users of a file system are to access shared file simultaneously. So in particular, they specify when modifications of data by one user will be observable by other users. And these semantics are typically implemented as code with the file system. The consistency semantics is directly related to the process synchronization algorithms we have discussed. I believe it's in chapter 6. However, the complex algorithms of that chapter tend not to be implemented in the case of the file input-output because of the great latencies and slow transfer rates of disks and networks. For example, performing an atomic transaction to a remote disk could involve several network communications, several disk reads and writes, or both. And systems that attempt such a full set of functionalities tend to perform poorly. A full implementation of complex sharing semantics can be found in the Andrew file system, or the AFS. So for the following discussion, we assume that a series of file accesses, that is reads and write, attempted by user to the same file is always enclosed between the open and close operations, and the series of accesses between the open and closed operations makes up a file session. Okay? Now we also have what we call a unique semantics. Okay? And it uses the following consistency semantics. First is that it writes to an open file immediately to other users who have this file open. Now, one mode of sharing allows the users to share the point of current location into the file. Thus, advancing of the pointer by one user affects all sharing other users. Here, a file has a single image that interleaves all accesses regarding or regardless of their origins. We also have session semantics, or what we call the Andrew file system, or the Open AFS. The semantics involves writing to an open file by a user that are not visible immediately to other users that have the same file open. And once the file is closed, the changes made to it are visible only in sessions starting later. And it's already open instances of the file do not reflect these changes. So definitely it can be of several copies and each are changed independently. Now, talking about the NFS, or the Network File System, which is from the Sun Microsystem, NFS is both an implementation and specification of a software system for accessing remote files across local area networks or even wide area networks. So basically, NFS is part of ONC+, which most Unix vendors and some PC operating system support. The implementation described here is a part of the Solaris operating system, which is a modified version of the Unix SVR4, and it uses either the TCP or IP or the UDP protocol depending on the internetworking network. And the specification and the implementation are intertwined in the description of the network file system. So basically, NFS views a set of interconnected workstations as a set of independent machines with independent file systems, and its goal is to allow some degree of sharing among these file systems in a transparent manner. Sharing is based on a client-server relationship, and sharing is allowed between any pair of machines. So to ensure machine independence, sharing of remote file system affects only the client machine and no other machine. So a remote directory will be accessible in a transparent manner from a particular machine. Okay, so a client of that machine must first carry out a mount operation. So here, see here from the remote directory is mounted over a local file system directory, and the mounted directory looks like an integral subtree of the local file system, which replaces the subtree descending from the local directory. Okay, now to illustrate the remote directory, specifications for the mount operation is non-transparent, wherein the host name of the remote directory has to be provided. Okay, and the files in the remote directory can then be accessed in a transparent manner. Now, subject to access right accreditation, NFS is potentially any file system on a directory within a file system, and can be mounted remotely on top of any local directory. Basically, NFS is designed to operate in a heterogeneous environment of different machines, operating systems, and network architectures. And the NFS specifications are independent of this media. And this independence is achieved through the use of RPC primitives built on top of external data representation or XDR protocol, and it's used to between two implementation independent interfaces. Okay, furthermore, NFS specification distinguishes between the services provided by a mount mechanism and actual remote file access services. Now, to illustrate file mounting, consider the file system depicted in this illustration, where the triangles that you see represent subtrees of directories that are of interest, and the figure shows three independent file systems of machines U, S1, and S2. And at this point, on each machine, only the local files can be accessed. Okay? In this figure, you will see the effects. No, it shows the effects of mounting S1. Okay? In USR shared over SU. And this figure depicts the view users on U hub of their file system. After the mount is complete, they can now access any file within the dir directory using the prefix USR, local, and directory 1. So the original directory USR local on that machine is no longer available, no? As you can see from here. So this is the original. So when mounted, the USR local will not anymore be visible. The mount protocol establishes the initial connection, or the initial logical connection between a server and client. And in Solaris, each machine has a server process outside the kernel performing the protocol functions. A mount operation includes the name of the remote directory to be mounted and the name of the server machine storing it. So the mount request is mapped to corresponding RPC and forwarded to the mount server running on the specific server machine. So the server maintains an export list which specifies the local file systems that it exports for mounting, along with names of machines that are permitted to mount them. Alright? Now, when the server receives a mount request that conforms to its export list, the server returns a file handle, and this file handle is serving as a key for further access to any files within the mounted file systems. And the file handle contains all the information that the server needs, and that is used to distinguish an individual file it stores. And in Unix terms, the file handle consists of a file system identifier, an inode number to identify the exact mounted directory within the exported file system. The server also maintains a list of the client machines and the corresponding currently mounted directories. And this list is used mainly for administrative purposes. Okay? So basically, the mount operation changes only the user's view and does not affect the server side. The NFS protocol provides a set of RPCs for remote file operations, and the procedures support the following operations. So it can search for a file within a directory. It can read a set of directory entries. It also manipulates links and directories, access the file attributes, and read and write the files. So basically, NFS servers are stateless, which means each request has to provide a full set of arguments. The modified data must be committed to the server's disk before results are returned to the client. And the NFS protocol does not provide concurrency control mechanism. So this is a schematic view of the network file system, and NFS is integrated into the operating system via the BFS. And as an illustration of the architecture, we can trace an operation on an already open remote file. How does the NFS architecture handle the already open remote file? Okay, so basically the client is connected to the server via a network. Okay, so the client initiates the operation with a regular system call, for example, and the operating system layer maps this call to the BFS operation on the appropriate vnode. So the BFS layer, okay, identifies the file as a remote one and invokes the appropriate NFS procedure. An RPC call is made to the NFS service layer at the remote server, okay, here. And then this call is re-injected to the VFS layer on the remote system, which finds that it's local and invokes the appropriate file system operation. And this path is retraced to return the result. And an advantage of this architecture is that the client and the server are identical. Thus, a machine may be a client or a server or both, and the actual service on each server is performed by the kernel threads. Now, path name translation in network file system involves the parsing of a path name, such as, for example, the common, which is the slash user slash local, and then the directory and the file name, no? And it's separated into directory address or entries or components, namely the user component, the local component, and the directory component. So basically, path name translation is done by breaking the path into component names and performing a separate network file system lookup call for every pair of component name and directory vnode. And once a mount point is crossed, every component lookup causes a separate RPC to the server. And this expensive path name traversal scheme is needed, since the layout of each client's logical namespace is unique, dictated by the mounts the client has performed. Now, to make lookup faster, a directory name lookup cache on the client side holds the vnodes for remote directory names. With the exception of opening and closing files, there is an almost one-to-one correspondence between a regular Unix system calls and the NFS Protocol RPCs, except opening and closing files. Okay, so thus a remote file operation can be translated directly to the corresponding RPC, and conceptually NFS adheres to the remote service paradigm, but in practice it employs buffering and caching techniques for the sake of performance. There is no direct correspondence existing between a remote operation and an RPC. Instead, file blocks and file attributes are fetched by the RPCs and are cached locally. So future remote operations use the cache data subject to consistency constraints. And there are two caches, okay? The file attribute cache and the and this file attribute cache and the other one is the file blocks cache, no? So basically, when a file is opened, the kernel checks with the remote server to determine whether to fetch or revalidate the cache attributes. And the cache file blocks are used only if the corresponding cache attributes, okay, are up to date. Now, the attribute cache is updated whenever new attributes arrive from the server. Okay, so that is what the file attribute cache is. So tuning the system for performance makes it difficult to characterize the consistency semantics of the new file system. However, new file system provides strict emulation of Unix semantics. Okay? But in spite of these drawbacks, for example, the utility and good performance of the mechanism make it the most widely used multi-vendor distributed system in operation. So in summary, so we discuss about volumes, which contains the file systems that can be mounted in the computer file systems, and depending on the operating system, the file system space is mounted into the directory structure or distinct, wherein each mounted file system have its own designation. We also understood that at least one file system must be bootable for the system to be able to start. Okay? However, most systems are multi-user and must provide a method for file sharing and file protection. So we discuss about files, directories, which include metadata such as owner, user, and group access permissions. We also understood that mass storage partitions are used either for raw block, input-output, or for file systems. And to simplify implementation of multiple file systems, an operating system can use a layered approach with a virtual file system interface making access to possibly dissimilar file systems. And then we understood the remote file systems, which are implemented by using a program such as File Transfer Protocol or web servers. Okay, finally, we understood about the client-server facilities for sharing information in a distributed information system such as the DNS, we talk about also about the Microsoft CIFS, which uses Active Directory, and then we discuss about the network file system, which is an example of a remote file system which provide the clients with access to directories, files, and even entire file systems. The NFS is a full-featured remote file system that includes communication protocol with remote operations and path-name translation. So basically, that's the content or contents of the chapter 15. Thank you very much for your attention.